Hello, team. Hello, hello. Welcome to another edition of Miss Bowman Rambles On for about 45 minutes. We're going to be going over Unit 2, Day 2 today. So this video is in case you missed class today or you just want to go back through because you zoned out for a minute. We're going to go through the Day 2 notes and just kind of talk through the next part of derivatives. So if you remember from last class, we looked at the definition of the derivative and we looked at the definition as it relates to slope. So just to recall, oh, that's not a marker. There we go. We define the slope at a point, or the derivative of f at x equals a, as the limit as h goes to 0 of f of a plus h minus f of a all over a plus h minus a, or all over h. So that gives us the slope or the derivative value at fixed points, okay, which would be great. But if I gave you this function like x squared, and I said find the slope at 1, find the slope at 3, find the slope at -2, you are going to have to do the definition of the derivative over and over and over again, which just doesn't seem like it is efficient at all. So what we're going to talk about today is what if we can come up with a rule that would calculate the slope of x squared at any point we want to. In other words, what if we turn the idea of the derivative into a function itself, where I would input x values and the outputs of this function would be the slope at all these given points for a given f of x, okay? Well, in order to do that, that is 100% possible. All we have to do then is generalize how we calculate slope in general. So if I wanted to talk about find the slope at any point, that's finding f prime of x. That's saying any x value. Well, that would just be the limit as h goes to 0 of x plus h minus f of x all over h. So if I generalize the derivative definition to be in terms of x instead of in terms of a, then what that does is that this limit process will give me an expression, and that expression is going to calculate the slope at any point for a given function f of x. Now, I do want to do a little side note here to notice that we're using the formal first definition. The alternate definition that we talked about last class doesn't really apply here. So we're only going to use this limit as h goes to 0. We're not going to do the limit as x goes to a, because then it would be like the limit as x goes to x, and like that just doesn't even make sense. So we're going to use this definition and kind of look at this as a function itself. Now, f prime of x is going to be a derivative function. It's a function that measures slope. It has a domain, it has a range, and we're going to get all into the idea of how do we first find f prime of x, and then what's the relationship between f prime of x and the function f of x, okay? So those are going to be kind of the names that we're going to talk about for each of these. So we're going to go through and do a few examples where I'm going to give you a function f of x, then we're going to graph, or we're going to calculate the function f prime of x, and we're going to graph it on the same graph as f of x. As well, a lot of f's and f primes, it's easy to get confused. I was just trying to change my color here because I don't want to use blue, but I don't want to use red. I'm going to use green. That's it. Determined. Okay. So if I want to find an f prime of x function, that's going to be a function that would calculate the slope of f of x at any point. And so our f of x in this case is 3x. So what we're going to do to find f prime of x, we're going to take the limit as h goes to 0. Now, without the limit, guys, you are not finding the derivative. The derivative is a limit, okay? Everything's a limit in calculus. So we're going to take this and we're going to say, okay, I'm going to find f of x plus h minus f of x all over h. So what I'm going to do is where f of x is, I'm going to put the function. Now, this is like a little baby function. Make sure if that function has multiple pieces, like if it was like 3x plus 2 or 3x plus 7, that you distribute that negative in or put that in parentheses so you don't make a mistake. And then for this term in the front, I'm going to take my function, and wherever I see x, I'm going to plug in x plus h. So it's actually going to be 3x plus h and then minus 3x. So now I'm going to clean this up to find my derivative function. So I'm going to distribute, and I end up with that. Oh, look, these 3x's cancel. Isn't that magic? So now I have the limit as h goes to 0 of 3h over h. Oh man, those h's cancel. Isn't that nice? Well, now I just have the limit as h goes to 0 of the constant 3. There's no h left. I can't, if it says take the limit, that means I'm going to replace every h that I see with 0. Since there is no h, the limit is just going to be the constant. It's just going to be 3. So f prime of x is equal to 3. Sorry, excuse me. Okay, so this is my derivative function. You're like, Ms. Bowman, that derivative function is a number. Yes, it is. If I were to graph this function, this is like the line y equals 3. Guys, if I were to graph this, it would just be a horizontal line at a height of 3. This is my f prime of x graph. Now let's talk about why the derivative function is a constant and why the derivative function is a constant of 3. Let's investigate our regular function f of x, which is the blue line graphed here. That is a linear function. What do you know about linear functions? Well, linear functions have constant rates of change. They have a constant slope. Every point along this line has the same slope. That's the definition of a linear function. It has a constant slope. What is the slope of this line? It's 3. So what's my slope function? A constant at a height of 3. It all connects. So a linear function will have a constant function as its slope function. Okay, so here's what I want you to do. Example 2. Now I'm going to have you find the derivative function for f of x equals x squared, and then sketch that graph on top of the f of x graph. So pause, you know the drill. Pause me, unless you've never listened to my notes. Pause me, try this problem on your own, and then unpause me, and we will go over how to do it once I'm unpaused, okay? Okay, so unpaused me. I'm going to start by writing the definition. I write this definition every time because if I am a new student in calculus, I don't always, excuse me for 1 second. Okay. I don't always remember this definition. The more times you write it, guys, the better it's going to stick. So I make sure to write this every time. So now I'm going to take my function and I'm going to plug in x plus h where I see x. So I'm replacing x with x plus h minus, then I just have the function itself all over h. So now I distribute this out. Again, please don't tell me that's x squared plus h squared. If you did that, you know it happens to the best of us, but square that binomial the correct way. Every math teacher has a pet peeve, and that tends to be mine. Judgment-free zone, but I might fuss a little. Okay, so now I'm going to start cleaning up my expression. So if I look at this, my x squareds are going to cancel, which is nice. And I'm left with 2xh plus h squared all over h. Now I'm going to go ahead and see that there's an h in common here that's going to divide out. So I'm going to end up with 2x plus h, and there's really nothing in the denominator. I'm going to put a 1, but I honestly don't need the denominator. So now I can't simplify this anymore. So what I'm going to do is I'm going to take the limit. Now this is a really important key part to pay attention to. The limit is h goes to 0. There are 2 variables in this expression. We are replacing the h with 0. We are not touching the x. So the answer when I take the limit is actually 2x plus 0, which is just 2x. So what that tells me is the derivative function is equal to 2x. So this function, this expression, will calculate the slope at any point along this parabola that I would like to find. So if I want to find f prime of 1 for x squared, all I have to do is plug in 1, and I would get a slope of 2. That means that looking at this point has a slope of 2. If I plug in 0, 2 times 0 is 0, and I end up with a 0 slope. Okay, so if I were to graph this, we have a linear function with a slope of 2. Now, good mathematicians do look for patterns, and eventually we're going to talk about do we notice anything here? But looking at this graph, I do kind of want to talk about some key parts. If I look at this graph, the green line, that's my f prime of x graph. So any point along that line, the height or the y value of that point equates to the slope of the blue parabola at that point. So for example, at 1, I can see at 1, the point is at 2, so it's 1 comma 2 on f prime. That means that the slope of x squared at 1 is 2. So the outputs of remember the outputs of this derivative function are slopes of f of x. So I can see here we have a slope of 2, a slope of 4, a slope of 0. If I look at -1, that has a negative slope, and look at the derivative graph. In fact, in this whole section, notice how the graph of f of x, the blue graph, is decreasing this entire time. And if I look at just the green graph is on the negative side. So anytime my function f of x is decreasing, my derivative f prime of x will be on the negative side. Likewise, over here, the function f of x is increasing. So if I look at f prime of x is on the positive side. And then one key point, if I look here at the turning point of x squared at x equals 0, there is a 0 slope. That's going to end up being an x-intercept, a root, or a 0, whatever you want to call it, on the f prime graph. Okay, so I'm going to have you try one more on your own. So now that you've done x squared, let's do another parent. So we've done linear functions, we've done a quadratic function. And the last one I'm going to have you do by hand is x cubed. Okay, so I want you to find the derivative function for x cubed and then graph it, and we'll kind of talk about the graph and why it connects and makes sense. So pause me, try it, and then unpause me. Give you a second while I take a sip of water. Okay, welcome back. Glad you paused me and you just didn't let this play through. Okay, so here we have this. I'm going to take the limit as h goes to 0 of x plus h cubed minus x cubed over h. Now some of you are like, oh my gosh, Miss Bowman, did you really just have me do x plus h cubed? Yes. Is that the most efficient way to find it? No. I know my Pascal's triangle and binomial theorem, so I'm going to do this pretty quickly. 1, 3, 3, 1. Okay, so I see that. That's it cubed out. I've been teaching math 16 years, guys. That's why I know that by heart. I don't expect you to know that by heart. I don't expect you to actually multiply it out. But if I start cleaning this up, my x cubes will cancel, which is nice. So everything that I have left has an h in it. That's key. That's how you know you kind of did it right, is that the h's are going to have to cancel at some point. So since I have an h in the numerator in every single term, I'm going to divide out the h from the denominator. So that's going to give me 3x squared plus 3xh plus h squared. So that's the expression that I have left. And now I'm going to take my limit. Again, pay attention. The limit is h goes to 0. So in this expression, everywhere I see h, I'm replacing h with 0. So this becomes 0, this becomes 0, and I'm left with 3x squared. So f prime of x is the function 3x squared, which would look something like this, a parabola. Interesting. The cubic function gave me a quadratic function for its slope function. Interesting. We might build upon that later. Okay, now look. Let's talk about f of x here, the blue cubic function that I've graphed here. If you notice, this function increases the whole time, but it has a flat spot at 0. Look at my derivative graph. It's on the positive side above the x-axis the whole time, except at 0 where it touched and bounced off. So again, 0 slopes are going to be zeros on my graph. Positive slopes are on the positive side. And then we'll kind of get into more as we play through this unit and kind of look. So our goal throughout the rest of this unit is to kind of play with the derivative, learn how to interpret the derivative function, the domain and range of a derivative function, and so on and so forth. But let's keep going. So I want to use the derivative function from part A to write the equation of the tangent line at x equals 2. Now here is the coolest part. If I want to write the equation of a tangent line, remember the tangent slope is the same as the instantaneous rate of change. So the slope of the tangent line is the same thing as the derivative value at that point. So here's what my mantra for writing the equation of a tangent line. You're going to ask yourself, what do I need for the equation of a tangent line? And then you're going to answer yourself like a crazy person and say a point and a slope. So I know I need a point to write an equation of a line, and I need the slope to write the equation of the line. Okay, so if I need a point, and I'm writing the tangent line for f of x, which is the blue graph, okay? So I need to find the point at 2, so I'm going to find f of 2. So f of 2, if I look at my f of x equation, is x cubed, so it'd just be 2 cubed, which is 8. So my point is 2, 8. Wow, smart software is definitely failing me today. Okay, that doesn't even look like English. I need to erase this. Try again. Sorry, team. So we have the point 2, 8. There we go. That's a little better. Okay, now my slope. If I want the slope of the tangent line, I need the instantaneous rate of change. Well, I have a slope function. F prime of x calculates the slope at any point, so I just need to figure out what is f prime of 2. Well, I have this expression for f prime of x here. So if I plug in 2, this expression is what's calculating the slope for f of x. So I'm just going to plug 2 into my derivative function. And when I do that and simplify it, I get 4 times 3 is 12. That tells me that my slope is 12. So I have a point, I have a slope. Now I'm just going to put this in point slope form for the win. So it's going to be y minus 8 equals 12, because that's my slope, times x minus 2. And there is my tangent line. Okay. Could you do it in slope-intercept form? Yes. Should you waste your time bothering? No. Is that going to bother some of you? Yes, it is. But I'm going to tell you right now that as we continue on our calculus journey, the slopes are going to get more and more complicated looking, because we're going to have things like logs and sines and cosines and all that stuff. So point slope form is just the most efficient way we can get through it. Okay, team? Just trust me on that. So the key takeaway here is the tangent line is a good estimate for the point right around a given x value, because the slope of the tangent is the same as the slope at the point. So the derivative function is a slope function. It calculates the slope for any point for a given function f of x. Now, as we get talking about the derivative, I want to kind of go through all the different ways that we can say derivative in math. The prime notation, f prime of x, is probably the most common one because we use f of x a lot. So if we use f of x, then we'll say f prime of x. If it was g of x, it'd be g prime of x and so forth. So the prime notation is a very popular one. I'm going to go through 3 other names of the derivative and then 1 command form. So I know it's here, but I'm going to kind of write it so I can explain it why I write. So y prime is another way. So if I gave you like y equals 3x, then you could tell me y prime equals 3. So you could write it like that, and that means derivative. Okay, the other one are what we call Leibniz notation. And you're like, oh, I don't like this notation at all. But there is a benefit that we're going to go through later in the year for using this type of notation. So I just want to make sure that you can do it. Now, if you think about what the derivative is, it's a slope calculator. And if you think about what slope was rise over run from like grammar school. Okay, so it's the change in y over the change in x. So in calculus, a lot of times you might have seen this notation, change in y over change in x. That's the letter delta in the Greek alphabet. So it's delta y over delta x. So a lot of times for derivative notation, we'll write it as dy over dx instead of using the letter delta, because D is actually on a keyboard or a typewriter, which is, back in the day when they had typewriters, okay, the letter delta was not available. So they just wrote it as the letter D. So you would read this name as dy dx. So dy dx is the same thing as saying y prime. It's just saying it's the change in y with respect to the change in x, okay? Or we can just say the change in y with respect to x, or I would say the derivative of y with respect to x. Same thing with function notation. Instead of saying f prime, I could just say df dx. And I'm not going to say df over dx. I just read this df dx. Okay, and this is the derivative of f with respect to x, which just means that x is the independent or input variable. So if I had like a function f of t, for instance, I could write this as f prime of t if I wanted the derivative, or I could write this as df dt. Okay, again, because f is the name of the function, t is the independent variable. It's what the function is defined with respect to, so it's what the derivative will be as well. Now, those are different names for the derivative. There's also a command form for the derivative. So the last one is this d dx. This is not a name. By itself, this literally means nothing in mathematics, okay? This is a command saying find the derivative. So if you are using the command form, you always have to have something that comes after it. So I could write, for instance, I could say d dx of x squared. That's saying find the derivative function with respect to f of x squared, which would just be 2x because we've already done it, okay? I could also say d dx of the function's name, like f of x, okay? So regardless, when you write it as a command of what you're going to do or what they're asking you to find, there is an object after every command. This is for any command in mathematics. All commands in math have to be followed by an object. So like sine is a command. It's always followed by an angle. Log is a command. It's always followed by a value. So these things in math that are treated as commands always have objects that follow after it. D dx is a command. It follows the same with limit. Like if I just wrote limit x equals 2 equals 7, like that means nothing in math because there's no object here. Limits are a command asking you to find intended heights. So just make sure all commands are followed by objects. That's my soapbox. Okay, moving along. Keep it going. Now let's talk about when does a derivative exist? So the idea here is that we are going to figure out when a derivative exists and when it doesn't. So if I were looking at something, I would want to know if it has a derivative function. We would say that if the derivative exists at a point, that the function is differentiable. So we say f is differentiable at x equals a if f prime of a exists. And that kind of makes sense. It has to have a derivative in order to be differentiable. Now, when do we know a limit exists? Well, here's the first thing. F of x must be continuous. If it's not continuous, it's automatically not going to be differentiable. And we'll talk about that more next class. We're going to really get into differentiability, but here I'm just going to give you kind of the bones of it. Now, other than that, the derivative is a limit, okay? The derivative is a limit. So the question is, when does a derivative exist? It's really saying, when does a limit exist? Do you remember how to prove if a limit exists at a given point? I'm going to give you about 20 seconds to think it over. Pause me if you need to. The limit exists if and only if the limit from the left is the same as the limit from the right. It is no different here, okay? So a function has a derivative value. The derivative exists if the limit coming from the left for the derivative, aka the slope from the left and the slope from the right, both exist and are the same value. Okay, so we would say the limit as h approaches 0 from the left of f of a plus h minus f of a over h equals the limit as h approaches 0 from the right of f of a plus h. Wow, my smartboard is just not behaving. Okay, it really just means if I have the point A, I can go h spaces here, or I can go h spaces here. And if both of those give me the same limit, or both of those limits exist, then our function is differentiable. Okay. So let's look at the first example here of absolute value of x. Okay, so absolute value of x, if I want to show that the general derivative of absolute value of x doesn't exist, what I'm going to have to do is figure out what's the slope approaching 0 from the left and what's the slope approaching 0 from the right. Now, some of us get really confused with absolute value. Here's what I want to make sure that you know. Absolute value is really a piecewise function, okay? It's the opposite of x when x is negative, because the opposite of a negative number is a positive number, and it's just whatever x is when it's greater than or equal to 0. It actually doesn't matter which 0 you include, but I'm just including the positive one because it makes more sense to me. I don't want to take the opposite of 0. I just want to take 0. Okay, so if that's the case, what I'm going to do is I'm going to find the left slope. So I'm going to take the limit as h approaches 0 from the left. And now I'm going to find f of 0 plus h minus f of 0 all over h. Okay, so if I'm looking at this, f of 0, well, that's 0 because this is the point either way. So for f of 0, I'm going to get 0. If I plug in 0 plus h, now here is the clue, okay? I am coming from the left of 0 for the slope. So when I plug in 0 plus h, I'm actually going to plug it into the left function. So instead of negative x, I'm going to have negative 0 plus h. So now I have the limit as h approaches 0 from the left. And then I end up with negative h over h, which those cancel. It leaves me with a constant negative 1, which means the slope coming from the left is negative 1, which if you think about absolute value, the slope on the left side is negative 1. Okay. Now if I find my right slope, I'm going to take the limit as h approaches 0 from the right of f of 0 plus h minus f of 0, holy moly, all over h. Okay. So now my f of 0 hasn't changed. It's still 0, which is nice. But my 0 plus h is going to be different because if I'm coming from the right side, I'm going to have to plug in 0 plus h into the right side, which is just x. So I'm replacing x with 0 plus h. So I can see here my zeros are going to cancel. My h's actually cancel, and I end up with a constant of 1. And the limit of anything of a constant is that constant, so the slope is 1. So since the slope from the left does not equal the slope from the right, the derivative does not exist. So the left derivative doesn't equal the right derivative. Okay, and that's how you would prove if the derivative exists or not. Okay. I think that might have been it, actually. Oh yeah, that's it. So that's the notes for today. I hope you have a great day. Let me know if you have any questions. Come to office hours, email me, chat in the chat room. Otherwise, enjoy yourself.